So we are going to start our conversation about prisms, cylinders, pyramids, cones, and spheres by talking about cross-sections and solids of revolution. So we're going to talk about cross-sections first. A cross-section is the intersection of a solid figure and a plane. So if you think about a three-dimensional object, I don't know, for whatever reason, when I'm talking about this, I like to think about cakes. Maybe it's because my daughter's birthday is on Friday, so I'm thinking about like baking a cake. And you can do lots of different shaped cakes with different pans. And then the cross-section would be if you take a knife and you chop all the way through that cake. And then you look at the cut edge. So here we've got three different pyramids shown. In this one on the far left, the green plane is chopping horizontally through that pyramid. If I were to lift the top of the pyramid off, now that it's been cut, and I were to look at that freshly cut side, what two-dimensional shape would I see? There is a way to get a trapezoid, but not like that. This is a square pyramid. The base is a square. So as we come up on all the sides, they're coming up at the same rate. So if I chop through it horizontally and I look at that cut edge, I would see a square. If the sides were tipped a little bit, then we would get a trapezoid shape. If we go through it vertically, like over here on the far right, if I go perpendicular to the base instead of parallel to the base, and I chop down through the vertex, through the very top point of that pyramid, straight down to the bottom, again, perpendicular to that base, so making a nice right angle with the bottom there. If I were to cut through this pyramid like that, and then pull the two halves apart and look at that cut side, what shape would I see here? I'd see a triangle. It would be an isosceles triangle because this face and the back face that we can't see are congruent, so they'd be coming up at the same rate. I'd have two congruent sides and then the bottom part of the triangle there. A plane of symmetry is where I take a cross section, but I do it so that the two halves are mirror images of each other. You could kind of think of it as if you look at this picture at the bottom, this plane of symmetry is going right through the center of this rectangular prism, and I could take the right half and rotate it over on top of the left half, and they would match up identical. That is what a plane of symmetry is. So a cross section is just where I chop through the shape and I look at the cut edge. A plane of symmetry is where we chop through the shape so that we make mirror images on either side of this three-dimensional object. So I want to practice with some planes of symmetry here. I've got two examples for our planes of symmetry. Number one, we're looking at this rectangular prism. We want to describe in words each plane of symmetry for the rectangular prism, and then we want to give a total number of how many planes of symmetry this rectangular prism has. So the first plane of symmetry that I see when I'm looking at this rectangular prism, if I chop it right here, if I chop right through that rectangular prism horizontally, so that would be parallel to the bases, right through the center of those vertical edges. That would be one plane of symmetry. So there is one plane parallel to the bases. Through the center of the prism. So that's one plane of symmetry there.
I don't understand what you wrote.
So there's one plane, there's one cut that we could make that is parallel to the bases, the top and the bottom.
Okay.
So parallel, we're not going through it. We're never going to touch the top and the bottom. We are parallel to those bases through the very center of the prism. So if I go from the top to the bottom and I find the midpoint there, and I do that on all four of these edges, that's what I mean by through the center of the prism.
Okay.
Does that make more sense?
Yes.
Okay, so that's one plane of symmetry that we could have.
So, but do planes of symmetry ever go through the base?
Yes, let's actually look at a couple that'll go through the base. If instead of cutting it horizontally, parallel to the bases, I decide to go vertically, perpendicular to the bases. So now I'm going to cut through the top and the bottom. If I find the midpoint of the left edge and the midpoint of the right edge, so the exact halfway point for the left and the right edges, and I were to use that, I were to place my knife right here and then go straight down until I hit the midpoints down here for the left and the right edges. If I were to cut it like this, I would create a front and a back that would be mirror images of each other. Does that make sense? Planes of symmetry always have to cut it into two congruent mirror images. If it doesn't make mirror images, then it's not a plane of symmetry.
Okay.
So I could cut it like this. Could I cut it any other way and still be perpendicular to the base and cut it exactly in half? Yeah, instead of going left to right, we could go front to back. So I could find the midpoint of the front edge and the midpoint of the back edge, and I can cut through the top right here, straight down to the bottom, and then midpoint of the front edge, midpoint of the back edge. So if I were to cut it right here, I would create a left half and a right half that are identical. Does that make sense? Okay, so we're going to describe those two planes of symmetry. There are two planes perpendicular to the bases. Perpendicular to the bases means I'm cutting through those bases like straight down through those bases. Two planes of symmetry perpendicular to bases through the midpoints of the opposite sides. This is how I guarantee that it's cutting it in half. The bases on this prism, it says, are rectangles. It's called a rectangular prism. They kind of look like what shape? If you look at the top and the bottom. Well, they are rectangles. I know they're rectangles based on the name. But look at those rectangles. They kind of look like what other shape? I'm looking at the top and the bottom. They kind of look like squares. The top and the bottom kind of look like squares. Do we know that they're squares? No. If I knew that the top and the bottom were squares, so all four sides are congruent, then I could cut it diagonally as well. and go through opposite vertices, and I would create mirror images. But only if it's a square. If it's not a square, then I could still make that cut, but I would not get mirror image halves. They would be the same size. I'd still be cutting it in half, but they wouldn't be mirror images of each other. So I want to write that down here. If we knew the bases were squares, we can't assume that. Then there would be two more planes of symmetry. Perpendicular to the bases through opposite vertices. But as it stands, we don't know that the top and the bottom are squares. So I can't include those two planes. If I want a total number of planes, we have one that is parallel to the bases, and we have these two that are perpendicular to the bases that go through the middle points of the sides for the top and bottom. So I have a total of 3 planes of symmetry. Yeah, I drew it just a second ago. It would go diagonally corner to corner. All right, I drew it just a moment ago. So the ones that I'm talking about, the ones that we cannot say, we don't know, go like this. If I knew that the top and the bottom were squares, then that would be a plane of symmetry. And the one that goes through the other 2 corners would also be a plane of symmetry. But because I don't know the top and the bottom are squares, if I cut it like this, if that top is not a square, this point might not land on top of that point when I fold it over. That's why it wouldn't be a plane of symmetry. With this plane of symmetry right here, this corner right here would land on top of this corner. This corner right here would land on top of this corner if I were to rotate it up so that they stacked on top of each other. Okay. Does that make sense? Yeah. All right. Let's look at number 2. Let's try a different shape. Here I have a pentagonal prism. How many edges do the bases have? 5 edges. Because the top is a pentagon, 5 sides, and the bottom is also a pentagon, 5 sides. And notice that connecting the top and the bottom, we have rectangular faces. It's rectangles connecting the top to the bottom, but the top and the bottom are pentagons. That's what we mean when we say a pentagonal prism. All right, planes of symmetry here. Could I chop this one parallel to the bases right through the middle? Would that make a plane of symmetry? Could I cut it right here and end up with a top and a bottom that are the exact same size?
Not yet necessarily.
If I chop it through the middle?
Oh, wait, through the middle, yes.
Yes, if I chop it through the middle, halfway in between the top and the bottom, parallel to those bases, making sure that I make a straight cut, then that would be a plane of symmetry. So once again, we have one plane parallel to the bases through the center of the prism. When I'm looking at these prisms and I'm looking for planes of symmetry, I will always be able, on a prism, to chop halfway in between the top and the bottom, parallel to the top and the bottom, and get a top piece and a bottom piece that are exact same size and shape, that are mirror images of each other. So I'll always be able to do the one that's parallel. Now let's look if I go perpendicular to the base. So this would be if I take my cake and I cut the top apart from the bottom, and I lift the top part of my cake off. Perpendicular to the base, now instead of cutting through the center of the cake this way, I'm going to cut down through the top straight down to the bottom. Where could I cut on this pentagonal prism so that I would get, sorry, let me fix this. Where could I cut on this pentagonal prism so that I go through the top, all the way down through the body of the prism, and hit the bottom, and I cut it into two congruent mirror images?
I think you could start. I think it'd be better if I just showed you on my paper.
Sure, show me on your paper.
Yeah, so it would be better if you start here and go to the bottom of the pentagon, and then continue to go down, and then
Yes.
and then just.
Yep. I'm going to take that and draw what you just set up on the screen so that everybody else can see it. So what was just suggested is that I start by placing the knife or whatever I'm using to do the cutting right here on the point of the pentagon. And then I want to hit the halfway point of this side. So right here is how I would orient the knife to cut down through the center of this cake. And I would go straight down to the bottom, hitting the middle point here and hitting the point back here. Does that make sense? Then I would cut this into two congruent halves. So I can do it like that. Are there any other places where I could make a similar type of cut? Or do I have to go through that point and that edge? What'd you say? Does it have to be that one? That's my question.
I think one other thing you could also do is instead of starting from there, you can start from there, then.
Ooh, yeah, we could start from this vertex, and this would be the side that is opposite. Because of the perspective drawing on this, it doesn't look exactly like that's halfway, but that's just because of how we're standing looking at the picture. This pentagon has 5 congruent sides. So if I cut through the center of this side, that's exactly the same as if I cut through the center of this side. So I can cut through this corner and this edge straight down and cut it top to bottom this way, cutting it into 2 equal halves. So there's 2 planes of symmetry that I can do like that. How many points are there? There's 5 points and there's 5 sides, right? So I could start with the one that's all the way in the back, the point that's in the back, or I could do like that back left corner, or the front left corner, or the front right corner, or the back right corner. I've got how many corners to choose from when I'm going halfway through the cake this way? I've got 5 corners to choose from. So there are 5 planes of symmetry when I go perpendicular to the bases, when I go up and down like this. It doesn't necessarily always mean up and down, because I could take that prism and I could knock it on its side, and then perpendicular to the base would be this way.
Oh, okay.
But with it oriented the way it is here, perpendicular to the base would mean top to bottom. So there are 5 planes of symmetry. Perpendicular to the bases. Through a vertex. And the midpoint of the opposite side. So that gives me how many total planes of symmetry then? 6 planes of symmetry. 1 that is parallel to the bases, and 5 that are perpendicular to the bases. Nicely done. All right, so that's planes of symmetry. I want to talk about cross sections for just a minute. Yes? Mm-hmm. We talked about cross sections right at the beginning. A cross section, again, is after I make that cut, I'm going to look at the cut side and see what shape is there. So looking at this pentagonal prism again, if I go parallel to the base, so this way, horizontally, and I cut right through the center of that cake, and I take the top off, and I look down at that freshly cut side, what shape would I see?
You would see pentagon.
I would see a pentagon, yes. If I cut this parallel to the base, I'm going to see the shape of the base. What about if I cut perpendicular to the base, like what I have drawn up here? If I were to cut through this pentagonal prism, through the top, straight down through the cake until I get to the bottom, and then I were to pull those 2 halves apart, and I were to look at that cut edge, what shape would I see on that cut face?
I think it'd be more accurate to say what shapes because
We'd only have one shape. If I cut perpendicular to the base, there's only one shape that will show up. Not.
It isn't still a pentagon.
It is not still a pentagon. Look at the way I've drawn this.
Square.
Close. Rectangle. We're going to see a rectangle. Try it sometime. When you have something that is a prism, like some kind of food object, like a cake or something like that, cut down through it vertically and look at that cut edge. The top is going to be flat, the bottom is going to be flat, and the sides are going to be flat. So you would end up with a rectangle shape just on that cut edge. I'm not looking at the whole object. I'm just looking at the 2-dimensional shape that I got when I cut through it right there. All right. Let's look at another shape where we do the same kind of thing to it. Go ahead and flip the paper over. Now what shape do I have? I have a cone. If I were to cut parallel to the base, so like this right here, I take this cone, I cut it straight through left to right, and then I'm going to pick the top of that cone up, and I'm going to look at that freshly cut edge. What 2-dimensional shape would we see? A circle, yes.
Are we talking about on the base of that new shape?
Again, we're just looking at the 2-dimensional shape that we would see. So here, pull out like this right here. If I were to take it and cut it like this, right? And then I were to look at the shape that I got on that cut edge, that two-dimensional shape would be a circle.
Oh, okay.
Does that make sense?
Yes.
That's exactly what we're talking about. So we're going to cut it, and then we're going to look at that cut edge.
All right.
What about if instead of cutting it parallel to the base this way, we went perpendicular to the base, making sure to go through this very top point. So I'm going to take my saw, I'm going to cut through this cone, through the top point, all the way down to the bottom, making sure that it's a nice straight cut. And then I'm going to pull the two halves apart. What shape would I see? A triangle, yes. Fantastic. As you are working through some of these problems on the homework, if you're struggling to identify what that shape is, see if you can go and find a real-world object that is that shape, something that you can hold and touch and mess with to try to figure that out. Even more helpful if you can actually cut through it. All right, so that's talking about planes of symmetry and cross sections. I want to move on now to something called solids of revolution. A solid of revolution is a solid figure obtained by rotating a plane figure or curve around an axis. Who has ever taken a bag or a purse and swung it around like this? Anybody ever done that? When you do it really fast, it looks like it's a solid shape, right? If you take a bag or a purse, that like straight line, and you spin it around really, really fast until it blurs, what shape does it make? It makes a circle. So we're going to be looking at taking things that aren't just, a straight line like this and spinning it. We're looking at what kind of three-dimensional object would we get if I took this figure and I were to rotate it really, really fast. All right, so let's look at this one. Here, I have, it kind of looks like a square. I'm not sure if all the sides are the same, but at the very least, it's a rectangle, right? We're going to take this and we're going to spin it around this line right here. So this point right here would rotate down until it hit a bottom here, and then it's going to rotate back up. This point right here would rotate down until it hits its lowest point right here. And then it's going to rotate back around and back up to the top and go around and around and around and around and around. So this is going to come down here. This is going to come down here. And this edge will also be rotating. So what I just drew looks a lot like this, right? What shape is that?
Circle.
The ends are circles, not a trapezoid. I'm looking for a three-dimensional object. So a prism, a pyramid, a cone, a sphere, a cylinder. We're talking about three-dimensional objects, things that I can pick up like this, not just flat shapes.
Cylinder.
It's a cylinder. It looks like a can knocked over on its side, right? This would create a cylinder. What about if we were to take this triangle right here and spin it really fast around this line? This point right here is connected to my axis. It's not going to go flying out anywhere, right? That's like holding on tight to the thing that's spinning. But this corner is going to go flying around, right? It's going to come around like this. And then it's going to go back to where it started from. This edge would make that rotation also. What kind of a shape would that make if I were to spin that really, really fast? What three-dimensional object would that be? What'd you say? A cone. It would make a cone. Whenever I take an object and I rotate it around an axis, I'm going to have some piece of it that's a circle shape, right? On the cone, that would be this part right here. It makes a circle on the bottom. Here we rotated it around a horizontal axis, so I ended up with circle-shaped bases on the top and the bottom. If I take something and I rotate it, I'm never going to be able to end up with like square corners. It's always going to have some like circle piece to it as I'm drawing in that rotation. So far, so good? All right. That is everything that you need to do the front side of the homework. Homework's due on Monday. What we just covered is everything that you need to do the front side of the homework. We're going to flip the page, and we're going to keep pushing forward now. We're going to talk about this three-dimensional object. What is this shape called? A sphere. A sphere is defined as the set of all points in space, a given distance, the radius, from a given point, the center. So on my sphere, this arrow is pointing to the center. And from the center to the edge of the sphere is a radius. From the center to the edge of the sphere is a radius. If I go from edge to edge on the sphere and I make sure to go right through the center, what do you think we call that? Diameter, yes. If I take a cross section of a sphere, I take a plane and I slice through part of the sphere, like right here. It's going to make a circle. This is the intersection of a plane and a sphere. If I have a plane of symmetry on this sphere, so I cut right through the center of the sphere, I'm going to get the biggest possible circle cross section that I can from this sphere if I make sure to go right through the center of it. We call that a great circle. A great circle cuts the sphere into two, it's going to cut it into two half spheres, right?
Yes.
What do we call a half sphere? You guys might have heard this word in geography before. When you talk about a globe, what is half the globe called? A hemisphere. So the great circle cuts the sphere into two hemispheres. This is the cross section through the center of the sphere. So this right here would be a hemisphere, cutting it along that great circle and then taking just the bottom or just the top would be a hemisphere. right. What is this shape right here? Looks like a dome. What would the official name for it be? We just used it. Hemisphere, yes. This dome is a hemisphere. All right, let's talk formulas. The volume formula for a sphere is 4/3 pi r cubed. Volume gets cubed units. Four-thirds pi r cubed. And if we have units at the end, like centimeters, if I found volume, that would be centimeters cubed. Volume always gets cubed units. Surface area for a sphere is 4 pi r squared. And surface area gets squared units. Let's try one example together. We're going to flip the page. We're going to look at number 1. We're going to do parts A and B with our last couple minutes. What does the R mean in both of those formulas? Radius. So what do we have to do if they don't give us the radius, if they give us the diameter instead? Divide it by 2. That's exactly what they've done here on number 1. They gave us the diameter, so we need to find the radius. We're going to take 23, which is my diameter, and cut it in half. What is half of 23? 11.5. So there's my radius. Volume is 4/3 pi r cubed. So I would have 4/3 pi, and then parentheses, 11.5 cubed to the power of 3. On the yellow calculators, we've only been doing squared as exponents, right? The squared button is right here next to the 7. That's not the button that we want to use when we want to cube something. I want you guys to type in all of this until we get to the exponent. So 4/3 and then the pi button and then parentheses 11.5 and close the parentheses. And then the button that we want to use to put in the exponent of 3 is the one just above the x squared key. It looks like the top part of a triangle or like part of an arrow. It's called a caret. Right above the x squared key, you're going to push this button, and then it'll have a little flashing cursor up where the exponent goes, and you're going to type in the 3. Does anybody have a volume that they can give me? 6370, you said 0.626? Yes, and then the button right above the squared key is what you push so that you can type in your own exponent. Did you find it?
Yeah.
Okay. 6370.626. All right, let's do surface area and then we'll call it a day. Surface area is 4 pi r squared. So 4 pi times the radius of 11.5 squared. What do we get when we do that? 1661 point. You said 902? And that would be centimeters cubed or squared? Squared. For surface area, this is just like all the other area problems we've done. Surface area gets squared units. Right. We will finish up page 4 tomorrow in your notes. And then you guys will have a good chunk of class time tomorrow to work on the homework. All the sphere stuff is on the back of the homework. The front of the homework, you can do all of that already. Homework is due on Monday.